Welcome to the first session of the course. Before we talk about what these tools can do for you, we need to talk about where they came from. I know that sounds like the kind of history lecture you sit through waiting for the useful part. Stay with me, because this one pays off immediately. Here is why. Almost every bad decision I have watched a clinician make about artificial intelligence comes from having the wrong mental model of what the technology is. People who think it is a database get frustrated when it invents a citation. People who think it is a doctor get frightened when it is confidently wrong. People who think it is magic stop checking its work. By the end of this hour, you will have a mental model that is roughly correct. Not a computer scientist's model, a clinician's model. Good enough to predict in advance what these tools will be good at and where they will fail you. We are going to move through 50 years in 4 acts: the rule era, the learning era, the transformer era, and then the product moment in 2022, which changed almost nothing technically and changed almost everything practically. 60 minutes. Let us start.
3 objectives for the hour. First, you should be able to explain the shift out loud to a colleague. Not recite a definition. Explain it. If you can tell a fellow over coffee why an expert system and a large language model are fundamentally different kinds of thing, you have got it. Second, you should be able to say clearly what changed in 2017 and what changed in 2022. These were completely different kinds of event. One was a technical paper that almost nobody outside the field noticed. The other was a product launch that changed nothing technically. People blur these together constantly, and the blurring is why so much of the public conversation about artificial intelligence is confused. Third, you should be able to place the tools you already use somewhere on that timeline. This one surprises people. Some of the artificial intelligence running in your neonatal unit right now is older than your fellows are. It is not the same technology as the chatbot you used last week, and treating them as the same category leads you astray. I want to be honest with you about something. This session has no clinical content. There is no workflow you can implement tomorrow morning. Every session after this one does have that, and several of them will save you real hours in your week. But this is the session that gives you the vocabulary the other 40 are written in. Skip it, and everything downstream is vaguer than it needs to be.
2 dates. If you remember nothing else from this hour, remember these. June 2017. A group of researchers at Google publish a paper called "Attention is All You Need." It introduces an architecture called the transformer. At the time, it was read by a few thousand specialists. There was no press coverage. It was a paper about machine translation. That paper is the technical origin of every tool we will use in this course. Claude, ChatGPT, Gemini, the image models, the video models. All of them are descendants of that one architecture. November 2022. OpenAI puts a free chat interface in front of the public. Within 2 months, it reaches 100 million users, which was at the time the fastest adoption of any consumer product in history. Here is the thing people get wrong. Technically, almost nothing new happened in November 2022. The underlying model had existed for months. The architecture had existed for 5 years. What changed was access. Somebody removed the friction between an ordinary person and a capable model. And it turned out that friction was the only thing holding the whole field back from public awareness. 5.5 years separate the capability from the access. Almost everything people call the artificial intelligence revolution actually happened during that gap, quietly, in research labs, while none of us were paying attention. Why does this matter to you clinically? Because it tells you the pace is not slowing. The gap between what is possible in a lab and what is on your phone has been closing steadily. Things that seem 5 years away are often 18 months away.
Act 1. Roughly 1970 to 2000. In this era, the way you built an intelligent system was that you sat down with an expert. You asked them how they made decisions, and you wrote those decisions down as rules. If the white cell count is above this and the temperature is above that, then consider this diagnosis. This is called an expert system, and I want to be clear that it was not stupid. It was a completely reasonable idea, and for narrow, well-defined problems, it genuinely worked.
It also died. Understanding why it died tells you a great deal about why the current generation works. Let me give you the canonical example, because it is genuinely instructive. Mycin was built at Stanford through the 1970s. It diagnosed bacterial infections of the blood and recommended antibiotic therapy. It contained roughly 600 rules, and every single one of those rules was extracted from a human infectious disease specialist through interviews. Somebody sat with an expert and asked, "How do you decide?" and then wrote it down as a formal rule. It had a feature that modern systems still struggle with. You could ask it why. Why are you asking me about the patient's recent surgical history? And it would tell you which rule it was trying to evaluate and why that mattered. Full transparency, complete auditability. Every conclusion traceable to a specific rule written by a named expert. And in blinded evaluation, Mycin matched or outperformed Stanford infectious disease faculty on therapy selection. This is not folklore. It was published. Now look at the number on the right. 0. Mycin never treated a single patient. It was never deployed clinically. Why not? Partly liability, which was genuinely unresolved. Partly integration, because in 1979, there was no electronic health record to plug into, and a clinician would have had to type every value in by hand at a terminal in another room. But mostly maintenance. 600 rules sounds manageable until you realize that antibiotic resistance patterns change, new drugs arrive, guidelines shift, and every one of those changes means somebody has to go back through the rule base and work out which rules are now wrong and whether fixing one breaks another. There was no funded team to do that. So it sat there, technically excellent, and slowly became out of date. Hold on to that. The failure mode was not accuracy. It was maintenance. 3 reasons the rule-based approach could not survive, and they generalize beyond Mycin. 1. The knowledge bottleneck. Every single rule had to come out of a human head and get written down by hand. Expert clinician time is the scarcest resource in medicine. If you want the system to cover twice as much ground, you need twice as many interview hours. It scales linearly with the most expensive input you have. That is a losing position. 2. Brittleness at the edges. Rules cover the cases somebody thought to write a rule for. Medicine is largely edge cases. Think about a 24-week infant with an unusual congenital anomaly and a family history nobody has documented before. A rule system faced with a combination nobody anticipated does not degrade gracefully. It either produces confident nonsense or falls over entirely. Humans handle novelty by reasoning from analogy. Rule systems cannot do that. 3, and this is the one that actually killed them. Maintenance debt. Medical knowledge decays. Every guideline update means somebody has to audit the entire rule base and check for interactions, because rules interact in ways that are not obvious. The cost of keeping a rule system current grows faster than the system's usefulness grows. Eventually, the maintenance burden exceeds anyone's willingness to pay for it, and the system quietly dies. Now, here is the insight that unlocked everything that followed. Instead of asking an expert to describe how they decide, which is slow and which experts are famously bad at anyway, show a system enough examples of their actual decisions and let it work out the pattern itself. That is the whole idea of machine learning in one sentence. Learn the rules from the data instead of writing them by hand. Act 2, roughly 2000 to 2016. Something worth saying up front because it reassures people. You already understand the core idea of machine learning. If you have ever fitted a logistic regression, you have done machine learning. You gave an algorithm some inputs and some outcomes, and it worked out the coefficients that best predict one from the other. Nobody wrote those coefficients by hand. The data determined them. Everything in this act is that same idea, taken much further than logistic regression can go. Let me put the two approaches side by side, because the contrast is the whole point. On the left, rule-based. A human decides what matters and writes it down. The system does exactly what it was told and nothing more. It is fully transparent. Every output traceable to a named rule written by a named person. When it meets something unanticipated, it fails loudly and obviously. And updating it means editing rules by hand. On the right, learned. The system finds what matters from labeled examples. This means it can pick up patterns no human ever articulated, which is the great strength. It also means it picks up patterns nobody wanted it to learn, which is the great weakness, and we will spend a whole session on that in Module 9 when we talk about bias. Learned systems are largely opaque. You can measure how well one performs. You often cannot say why it produced a particular output for a particular patient. Now look at the fourth row on the right, because clinically this is the one that matters most. Learned systems fail quietly. A rule system, given input it cannot handle, throws an error. A learned system, given data unlike its training set, produces an answer. A confident, well-formatted, completely wrong answer, with no signal that anything has gone wrong. Think about what that means operationally. A model trained on a North American neonatal population, deployed in a unit with a different case mix, different gestational age distribution, different ethnic makeup. It does not tell you it is now out of its depth. It just gets quietly worse, and unless somebody is actively monitoring its performance against outcomes, nobody notices. Silent failure is much harder to govern than loud failure. Remember that phrase. It comes back in session 19 when we discuss patient safety, and again in session 36 on bias.
2012 is the year the approach stopped being theoretical. There was an annual competition called ImageNet. The task was simple to state. Given a photograph, classify it into one of 1,000 categories. Is this a dog, a car, a mushroom, a stethoscope? Researchers had been grinding away at it for years, and progress came from careful hand engineering. Someone would design a better way to detect edges, or corners, or texture, and the error rate would drop by about a percentage point. In 2012, a team entered a deep neural network called AlexNet. Note the word deep. It just means many layers stacked on top of each other. And instead of a percentage point, it dropped the error rate by around 10 points in 1 year. Look at the numbers along the bottom. About 26% error before 2012, about 16% with AlexNet. By 2015, around 3%, which is below the measured human error rate on the same task. Two things made this possible, and neither was a new idea. Neural networks had existed since the 1980s. What changed was that we finally had enough labeled data because of the internet, and enough cheap parallel computing power because of graphics cards designed for video games. The theory had been sitting there waiting for the hardware. That is a pattern you will see again. Very often the idea is not new, the conditions that let it work are new. Why does an image competition matter to a neonatologist? Because the moment a computer could reliably classify a photograph, every specialty that looks at images became a target. Radiology, pathology, dermatology, ophthalmology. And ophthalmology is where neonatology got involved. Medicine followed quickly, and the regulatory record shows it. This chart is an approximate count of artificial intelligence and machine learning-enabled medical devices authorized by the American regulator each year. 6 in 2015, around 220 by 2023. That is not a gentle slope. That is a field arriving. But look at the panel on the right, because the headline number is misleading in 3 important ways. First, roughly 3/4 of those devices are radiology. Chest films, mammograms, head scans. This is not artificial intelligence spread evenly across medicine. It is heavily concentrated in one specialty, for the straightforward reason that radiology generates enormous volumes of labeled images. Second, almost all of them are narrow. A single model doing a single task. Detect this one finding on this one type of image. They are not general reasoners. They do one thing. Third, and this is the one I want you to hold on to, almost none of them have randomized evidence of patient benefit. Regulatory clearance in most cases means the device performed acceptably against a reference standard on a retrospective dataset. It does not mean anyone has shown that using it makes patients better off. Clearance is not proof of benefit. We come back to this hard in session 37, when we read an actual clearance document together and work out what it does and does not say. And notice what is almost absent from that pile. Language models. The chatbots you will use in this course are, for the most part, not regulated as medical devices at all. That is a deliberate regulatory line, not an oversight, and session 37 explains exactly where it sits. Neonatology got involved earlier than most people realize, and the story is worth telling because it shows you the shape of a problem that artificial intelligence solves well.
retinopathy of prematurity. Diagnosis depends heavily on grading plus disease, which is a subjective judgment about vascular tortuosity and dilation in the posterior pole. And there is a well-documented, slightly uncomfortable literature showing that expert graders disagree with each other on the same images more often than we would like. Treatment decisions hang on that grade. So the problem was real. There was a genuine gap that technology could fill. Second, the data existed, and this was almost accidental. Telemedicine screening programs had been capturing digital fundus images for years, with expert grades attached, because that is how telemedicine screening works. Somebody had already done the labeling for entirely different reasons. Third, the result held up. From around 2018, deep learning severity scoring systems were published that matched or exceeded individual expert graders. And they offered something humans genuinely cannot do reliably, a continuous, reproducible severity score instead of a category. You could track a number over serial examinations, rather than arguing about whether something crossed a threshold. Now, the key idea at the bottom. Look at the shape of that problem. High volume, image-based, imperfect human agreement, so there is room to improve, and abundant labeled data that already existed. Here is the uncomfortable part. Very little of your week looks like that. Most of neonatal practice is conversation with families, judgment under uncertainty with incomplete information, and physiological reasoning that unfolds over hours and days. There is no clean label. There is often no ground truth for months or years. Which is precisely why the language models are the more interesting development for you than the imaging models are. They operate on the stuff that actually fills your day. That is the argument for this entire course, and it is why we spend 4 sessions on prompting and only 1 on neonatal imaging systems. Act 3, 2017. We are now at the papal. Attention is all you need. I am going to explain this without any mathematics, and I want to set expectations about what you are getting. This will be a simplified account. A machine learning researcher would add caveats, but it is not a wrong account, and it is enough to reason correctly about how these tools behave. Here is the problem transformers solved. Before 2017, models that handled text read it the way you read a sentence, one word at a time, left to right, carrying a running summary forward as they went. This is called a recurrent architecture. 2 problems with that. The first is that by the time you reach the end of a long passage, the beginning has faded. The running summary has been overwritten many times. Ask such a model about something mentioned 3 paragraphs ago, and it struggles. The second problem is subtler and more important. Reading strictly in order cannot be parallelized. You cannot process word 50 until you have processed word 49. And that puts a hard ceiling on how large a model you can practically train, because training time scales with sequence length, and you cannot throw more hardware at it. The transformers move was to abandon sequential reading entirely. Instead, every word looks directly at every other word, all at once, regardless of how far apart they are. The model learns which other words to weight heavily when interpreting each word. That learned weighting is what the word attention means. It is not attention in any psychological sense. It is a set of numbers saying how much each word should influence the interpretation of each other word. Now, both of those benefits are real, but I want to be clear about which one mattered more. It was not the long-range dependency handling, useful as that is. It was the parallelization. Suddenly, you could train on much more text using much more hardware. And it turned out that when you did that, the models did not just get incrementally better. They started doing things nobody had trained them to do. The architecture was the enabler. Scale was the payoff.
Let me make attention concrete with a clinical sentence. The infant was extubated on day 4, and she tolerated it well. To interpret the word she, the model has to work out what it refers to. It should weight the word infant heavily, and the words day 4 barely at all. Nobody wrote a rule that says pronouns refer back to the nearest preceding animate noun. It was learned from reading enormous quantities of text where that pattern holds. And notice the word it in tolerated it well. That refers to extubation, which is a process described by a verb, not a noun. Resolving that requires something closer to understanding than to pattern matching, and this is the kind of thing older models were quite bad at. Now scale it up. In a discharge summary, a sentence like, "The infant remained on it for 6 weeks," might require reaching back several paragraphs to find what it refers to. Attention makes that reach cheap and direct. There is no running summary to fade. And then scale it up again to your whole conversation with the model. Everything in what we call the context window is available to influence every word being generated. Your original instruction, the document you pasted, the correction you made 4 messages ago, the example you gave, all of it, weighted all the time. This is the mechanical reason that how you set up context matters so much, and it is why Session 5 on the anatomy of a prompt is arguably the most useful 60 minutes in this entire course. It is also, and I will flag this now because it comes up constantly, the mechanical reason these models can be led astray. If you put a wrong assumption in your context, attention faithfully weights that wrong assumption into everything that follows. The model is not being stupid. It is doing exactly what it was built to do, with bad input. We spend a whole session on this in Session 8.
Then people made them very, very large. A quick definition first. A parameter is one adjustable number inside the model. During training, all of these numbers get tuned. More parameters means more capacity to store patterns. It is a crude measure of size, but it is the one everyone quoted for a while. 2018, BERT, 340 million parameters. It understood text well. It could not hold a conversation. 2019, GPT-2, 1.5 billion. It wrote fluent paragraphs. It was initially withheld from public release because the researchers were worried about misuse, which reads as quaint now. 2020, GPT-3, 175 billion. And here something genuinely unexpected happened. It started following instructions it had never been explicitly trained to follow. You could describe a task in plain English, in the prompt, and it would attempt it. Nobody built that in as a feature. It emerged from scale. 2022 onward, frontier models. And notice the symbol rather than a number. The company stopped publishing parameter counts, partly for competitive reasons, and partly because the numbers stopped being meaningful. Capability now depends on training data quality, on the fine-tuning process, on how the model is prompted at inference time. A well-trained smaller model routinely beats a poorly trained larger one. Now read the key idea at the bottom, because this is the part that should give you pause. Somewhere in that progression, these models started doing things nobody trained them to do, translating between language pairs that never appeared together in training, writing working code, passing medical licensing examinations. Nobody predicted those thresholds in advance. They were discovered after the fact by people poking at models that had already been built. And nobody can reliably predict the next one either. That is not me being dramatic. It is the honest state of the field, and it is a large part of why the governance discussion in Module 9 is difficult. It is hard to write policy for a technology whose next capability you cannot forecast. Act 4, November 2022. I have called this the product moment rather than a technical moment, deliberately. And I want to defend that framing because it is the single most useful reframe in this session. Look at the left column first. What did not change? The architecture was 5 years old. The underlying model had existed for months, available to developers. The capability was not new. People building software had been using it through a programming interface for some time. And the failure modes? Every single problem we will spend Session 8 on, hallucination, sycophancy, fabricated citations, all of it was already known and documented in the research literature. Now the right column. What did change? A chat box. That is genuinely most of it. No code, no setup, no cost, no application form. You typed and it answered. Conversational memory across turns. So you could say, no, not like that, more like this, and it would adjust. That turned a one-shot query tool into something that felt like collaboration. Refusal behavior and tone, shaped by an enormous amount of human feedback. This is the part people underestimate. The model was tuned so that talking to it felt like talking to something, rather than querying something. That is a design achievement, not an accident. and then 100 million users in 2 months, which means 100 million people simultaneously forming opinions about a technology they had never encountered, based on a few minutes of play, with no framework for interpreting what they were seeing. A great deal of the confusion in the public conversation dates from precisely that period. The lesson, and it generalizes well beyond artificial intelligence, removing friction is not a small thing. In medicine, it is often the whole thing. Think about how much of what limits the adoption of a good clinical tool in your own unit is not the tool's quality, but the number of clicks it takes to reach it. Hold on to that when we get to Module 8 and you start building things. The best assistant nobody can find is worth nothing.
3 things changed for clinicians specifically. This is the slide I would keep if I had to throw the rest away. 1. The interface became language. Every earlier medical artificial intelligence system required somebody to build a product around it. Somebody had to design a workflow, integrate it with the record, put it through procurement. A language model needs none of that. You describe what you want in words. This is why a consultant with no technical background can now build a working tool in an afternoon. That is not marketing. That is what Module 8 is, and you will do it in Session 31 with your own unit's protocols loaded in. 2. The tasks became general. The retinopathy model does retinopathy. It will never do anything else. A language model summarizes, drafts, explains, translates, critiques, coordinates, and does a dozen other things you have not thought of yet. That is enormously more useful. It is also a much messier governance problem, and I want you to sit with that discomfort rather than resolve it too quickly. You cannot validate a tool for all tasks. There is no study design that answers the question, is this safe, when the answer depends entirely on what you happen to ask it. This is genuinely unsolved, and Module 9 does not pretend otherwise. 3, and this is the one that should stay with you. The oversight burden moved to you. A regulated device arrives validated for a stated indication with a defined population, and somebody else has taken responsibility for that validation. A general-purpose model arrives validated for nothing in particular. Nobody has checked whether it is good at writing neonatal discharge summaries, because nobody knew that was going to be one of its uses. Which means the judgment about whether a given output is safe to use has been handed to the person holding the keyboard. That is you. Not the vendor, not the regulator, not your information technology department. If you take one thing from this session, take that. Everything we do in the remaining 40 sessions is in one way or another about equipping you to carry that responsibility competently.
Here is the whole thing on one line. 1972, Myson. Rules written by hand. Excellent, and never deployed. 2012, AlexNet. Learned features beat hand-engineered ones, decisively, and every image-based specialty became a target. 2017, the Transformer. The architecture behind everything since. 2018, deep learning for retinopathy of prematurity. Neonatology's own imaging win, riding the same wave. 2022, the chat box. Capability meets the public. And now, you. General-purpose tools and local judgment about how to use them. I want you to notice something about this line, and it is the point of the slide. Look at how little of it is about medicine. The Transformer was invented for machine translation. The scale that made these models capable was funded largely by search and advertising revenue. The image models were trained on photographs scraped from the open internet, not from hospitals. Medicine is a late adopter here, borrowing tools that were built for something else entirely. That explains a great deal about where they fit badly. It explains why a model can write a beautiful paragraph and get a drug dose wrong. It explains why the training data underrepresents your patient population. It explains why the safety tuning was designed with a general consumer in mind, not a clinician who needs frank discussion of a lethal condition. None of that makes the tools useless. It makes them tools, built for a different job, that you are adapting. Adapting a tool competently requires knowing what it was actually built for. Now you do.
Where does neonatology actually sit today? Here is my honest read, and Session 17 goes through every item on both lists with the evidence attached. On the left, mature enough to trust with appropriate care. Retinopathy severity grading from fundus images. Good evidence, widely deployed in screening programs. Heart rate characteristics monitoring. This one deserves special mention because it is the only neonatal artificial intelligence system I know of with randomized evidence of a mortality benefit. It is not new, it is not glamorous, and it is not a language model. It is a signal processing approach that has been around for years. Neonatal EEG seizure detection performs comparably to expert neurophysiologists, and it never gets tired at 3 in the morning, which matters. And retrospective research and audit work, where the stakes of an error are low and you can check everything. On the right, early, oversold, or unvalidated. Necrotizing enterocolitis prediction models. There are many published. Most fail when somebody tries them on a different population. We will look at why in session 3 when we talk about external validation. Neurodevelopmental outcome prediction for an individual infant. Population-level associations are real. Individual prediction is much weaker than the papers make it sound, and the gap between those two things is where families get hurt. Closed-loop ventilation and oxygen targeting outside of trial settings. Promising, not there yet. And the last one on the right, which I have phrased deliberately, anything a language model tells you about a specific baby. Not because it is always wrong, because you have no basis for knowing when it is wrong. And that is a different and much worse epistemic position than having a tool with known error rates. Now look at the two lists together and notice something uncomfortable. The honest list of things that work is short. 4 items. That should temper how you read the marketing material that lands in your inbox, and it should also tell you that the field is early enough that your own work could genuinely add to that left column.
10 minutes, in pairs, and then we will hear a few. List every piece of software in your unit that anyone has ever described as artificial intelligence. Then, for each one, place it in an era and answer one question. Was it built by writing rules, by learning from labeled data, or by generating language? I have put some likely candidates on the slide. Ventilator alarm logic. That is rules. An engineer wrote thresholds. Nothing was learned from anything. Calling it artificial intelligence is marketing. Infusion pump dose error reduction software. Also rules. A hard-coded drug library with limits. Retinopathy screening software. Learned from graded fundus images. EEG seizure detection. Learned from annotated recordings. Sepsis or deterioration risk scores? This is the interesting one. Sometimes genuinely learned from your institution's data. Sometimes it is a published regression equation with 6 variables that somebody implemented in the record system. Those are extremely different things with extremely different validity, and the interface looks identical. Find out which one yours is. That question alone is worth the exercise. Speech-to-text dictation? Learned and quietly rebuilt on transformers in the last few years, which is why it suddenly got much better at medical vocabulary. And anything with a chat box. Generative, and it arrived in the last 3 years. 2 things usually come out of this exercise. First, people discover that most of what gets called artificial intelligence in their unit is rules with good marketing. Second, people discover that genuinely learned systems are older than they assumed. Both observations are useful. Go.
3 things to remember. 1. Rules were written. Patterns are learned. Language is generated. 3 eras, 3 kinds of system, 3 completely different failure modes. A rule system fails loudly on cases nobody anticipated. A learned system fails silently on data unlike its training set. A generative system fails fluently, producing something that reads perfectly and is wrong. Most of the confused talk about artificial intelligence in medicine comes from treating these as one thing. 2. The architecture changed in 2017. The access changed in 2022. Keep those separate in your head. If you conflate them, you will make bad predictions about what happens next, because you will be watching product launches when you should be watching research. The capability has consistently run several years ahead of public awareness, and there is no reason to think that has stopped. 3. General-purpose tools move the oversight burden onto the user.
A cleared device is validated for a stated indication by somebody who took responsibility for that validation. A language model is validated for nothing in particular. Every time you use one clinically, you are the validation step. That is not a reason to avoid them. It is a reason to be competent with them, which is what the next 40 sessions are for.
Next session, we go one level deeper into how these things actually work. Session 2, what a large language model is actually doing. Tokens, context windows, temperature. Why the same prompt gives you a different answer the second time you ask. And why hallucination is structural, built into the mechanism, rather than a defect that somebody will patch out in the next release. That last point changes how you use these tools permanently, so do not miss it. 3 things before then. First, ask the same clinical question to 2 different models and keep both answers. Take a screenshot or paste them into a document. We use your own examples in session 2, and it lands much better with your material than with mine. Second, finish the tool mapping exercise for your own unit if you did not get through it just now. Bring the list. It becomes useful again in Module 9 when we draft governance policy, because you cannot write a policy for tools you have not inventoried. Third, read the glossary in the handout once. 25 terms. Every later session assumes them, and the ones about prompt engineering assume them heavily. Questions now, or bring them to session 2. Thank you.